The central isthmus is the primary target for ablation. This is very ablation centric. It's about how do you find the spot to be able to kill off the VT. The outer loop is the part that is on the racetrack. It is on the racetrack, it's on the circuit, but there is an area in which it's not completely confined or constrained by fibrosis. Therefore, when you pace from here, you will get fusion. Bystander is two types. There's remote bystander, which is if you're pacing in the right ventricle and it's an LV tachycardia, that's remote. And then there are adjacent bystanders, which are also called dead end pathways, which are connected or attached to the central isthmus. So there's two types of bystanders. And then there's the inner loop, which most people don't talk about. It's really kind of the same as an entrance site, but the idea is it's kind of like having an outer loop with a figure of 8 model, but this explains those that have long stemmic QRS that have concealed fusion. This is borrowed from Bill Stevenson, very elementary cartoon in which where you are pacing from approximates the distance from the circuit. Now, the only reason why this is a little bit inaccurate is because it's not purely distance, it's actually the conduction velocity. You can be a very short distance from the circuit, but you get a long PPI because the conduction velocity is so slow. So remember, we always think, oh, well, you can take the PPI minus TCL, divide that by 2, and that's basically kind of your distance from the circuit. But you could be 2 millimeters away, but 50 milliseconds in terms of the propagation time. And that seems very, very long. So that's the one word of caution. And then obviously, if you are in the circuit and pacing there, the collision between the anti and the orthodromic wavefront is completely contained within the circuit. And therefore, you can only exit out where the VT would exit. And that is why your QRS looks identical to the VT itself when you're overdrive pacing within the circuit. It is important to note that there's 3 types of capture. You can capture the direct local electrogram of interest. So people use different phrases for this. I call it direct capture or local capture. You can also capture downstream, which is the antidromic capture. I'm sorry, upstream. And then in the direction of the tachycardia is orthodromic capture. So that's like saying you're accelerating a potential way ahead of the pacing stimulus. That's orthodromically captured. But you're not directly captured with the pacing stimulus in the sense that it's being recruited and essentially obliterated within the pacing stimulus itself. That's kind of direct local capture. Hopefully that makes sense to everybody. This is the way in which these are the exact responses to entrainment. Hopefully I'll review again at these spots. So if you're outside the circuit, which is remote bystander, very distant, you're gonna see fusion and the PPI is gonna be long, obvious. If you're in the outer loop, you are on the circuit, so your PPI is within 30 milliseconds of your TCL, you're on the racetrack, but there is overt fusion because the pacing wavefront has antidromic capture of an area because it's not completely constrained by regions of fibrosis. If you're inside the circuit, you will have concealed fusion. Then you look at your stim to QRS and your EGM to QRS to be able to give you some sense that if you have a long stim to QRS, you're either at a bystander or you're at an entrance site. But if your PPI is long, then you have to be at a bystander. And again, that's called a blind loop or a dead end. The isthmus is the PPI and the TCL should be the same. The stim to QRS and the EGM to QRS should be the same because that means the area that you are recording from is exactly the one that you are capturing. And the central isthmus is 30 to 70% of that tachycardia cycle length. The entrance, which is proximal, is greater than 70%. And the exit is less than 30%. And this is all in relation to just being at the, all in relation to the onset of the QRS. So that's why we often call things that are 10, 20 milliseconds before the QRS pre-systolic, and things that might be 100 milliseconds before the QRS as diastolic. And then the inner loop is just good PPI, long stim QRS. All right, let's get to some of these. Let's get to some of the tracings here. This is the reference, Jack 1997. Seminal reference to review. 30 to 70 is the kind of what we look at in terms of separating your TCL. Again, the exit is what we think about is what defines the QRS. That's the onset of the QRS. So everything is timed to QRS onset to QRS onset. And then this is a really nice summary of everything I just went through. But again, in your mind, if you start with the 12 lead, which is how we teach all fellows of how to start interpretations, you will quickly know if there's overt fusion, it can't be a good spot because you have to be either way out as a remote bystander, or you might be in an outer loop, which means you're close, and that's how you assess that then by PPI, TCL. So this I will open up to a little bit of a pimp question, so you can unmute if you want to respond. Which one of these, this is a nice linear catheter during VT, is mid-diastolic? Any one of the fellows, unmute. LV 1, 2, 3, 4, you've got 10 options. Which one is mid-diastolic? Let's say I want to say 50% of the tachycardia cycle wave. If nobody says anything, I'm going to pimp Winterfield.
5, 6, 7, 8.
Zenith said 5, 6, 7, 8 is mid-diastolic. Can we get a Northwestern fellow that would say that's crazy, or is he spot on? Can you guys see my arrow? Maybe, maybe not.
Yeah, we can see it. We
Okay.
can see that. Yeah.
Northwestern fellows? Brad, get your crew to wake up, maybe?
Yeah, I would agree. That's reasonable as
Maybe 7,
mid-diastolic.
8 looks mid-diastolic. Perfect. So that's exactly what I was hoping you guys would say. Because mid-diastolic by the Stevenson idea, which is mathematical, it's 50% of the TCL, is as follows. So if we divide this up, and this is how we've been doing a lot of the high density delineation of the circuit, you divide the whole cycle length into 8 isochrones, you window it by onset. Take a look to see exactly where the middle of the window is. Bang, right there, 50, it's LV1, 2. So we typically will see that and call that early diastolic because it seems just so early in diastole. But remember, it's from the QRS onset. So your eye just sees after the QRS to the onset of QRS. And we've kind of always said diastole is that. So a lot of the times of what people call mid-diastolic, like let's say 9-10, is actually pre-systolic. In order to be mid-diastolic, it's actually usually after just the prior QRS. It's almost like a late potential, which are what we call sinus rhythm, but it looks just after the QRS onset. Does that make sense to everybody? That's mid-diastolic by the mathematical definition of dissecting the TCL? Any questions on that? Good. Then you've got the entrance, which is early. Entrance activation occurs inside the QRS. Exit activation occurs just pre-systolic before the onset of the QRS. So this is really nice to be in the era of multi-electrode catheters, to be able to get all these electrograms and then really be able to dissect out which components of the circuits you have by activation mapping, and then complement that with entrainment mapping. And I know that there's a whole debate on whether activation mapping is better than entrainment mapping, vice versa. I'm happy to take on Josh Cooper, who really loves entrainment mapping. We love activation mapping, even though I'm giving an entrainment talk. I think they're complementary, but our preference has certainly been in the era of high resolution mapping to do activation mapping first, try to get the whole circuit, and then as a bonus, do entrainment mapping, because we know one of the limitations is that you can disrupt it, you can terminate it, you can accelerate it, you can transition it, and sometimes it takes you're wasting 30 minutes of your time and giving program stimulation in a tenuous VT patient. People forget that when you're doing program stim, sometimes you flatline a patient if you look at the A line. So clinically, even induction itself is a hemodynamic perturbation. Okay, so this is the area of interest. The 3-point checklist, when you're going through all of these interpretations. 1, start with the surface. Is it identical to the VT? Is it a cut and paste job? If not, it's not concealed fusion. It's that simple. 2, PPI to TCL. That's really easy. But it's not when you can't tell which part of the electrogram is captured. So that's where we'll get into a little bit more. And then the stim to QRS, the only reason we really do this is to make sure you know where in the TCL, as a percentage TCL this is it proximal or is it distal? And then it really comes into play when we're talking about attached adjacent bystanders, blind loops, dead ends, because there the stim to QRS should exceed the EGM to QRS, and we'll talk about why that is. Here is just the Stevenson model on a trichrome stain here with fibrosis, just to give you a sense of something that looks like a more realistic. And then obviously, if you had plunge electrodes in here, you would trace diastolic activity. We're looking for this. And when you find this, this happens quite easily. And this is like a pathway. It goes away that quickly if you can find that protected isthmus. These are the 3-point checklist. 1, here you go. QRS looks identical. Here's the last captured beat. Here's the VT. Identical, cut and paste job. Let's now look at the PPI, 590, TCL, 590, checkpoint 2, 3, stim to QRS, EGM to QRS. Here's my pacing to my QRS onset is 190. My EGM, what I'm recording to here, also 190, perfect. 3 out of 3 on your boards that Brad helps a lot with. They will give you a perfect one here as well and just have you circle, is this a good spot? Perfect, keep going, not. But this is perfection in terms of the 3 criteria. Fusion can be confusing because we always do this with a single electrode or one big large tip catheter. But I think that multi-electrode pacing or electrode catheters can really shed new light on this. Here's entrainment, and here's a linear catheter, and you can see that we've got activation of diastole. We're recording a good spot, and that's what it looks like in VT. What does it look like when you're trying to overdrive pace in an attempt to entrain? Well, here is what it looks like when you're pacing. Does it look the same on surface? No. Look at lead 1. There are subtle differences where lead 1 is not a cut and paste job already. And you can see it's very rounded during pacing. So you can already tell there is overt fusion. It's also called manifest fusion. Same thing. Why? Because take a look there. There's your antidromic wavefront from your pacing site. And this is your orthodromic wavefront going in the direction of VT. So the point of fusion is sitting there right in the center, which is why it looks chevron and C-shaped, but it's a perfect illustration of being able to see the whole antidromic wavefront rather than just conceptualizing it with multi-electrodes when you're on a spot that's got concealed, that does not have concealed fusion on intracardiac or surface. So intracardiac shows manifest fusion with multiple electrodes, and the surface also shows that manifest fusion. What about activation mapping? Well, activation mapping is something that we've been pretty passionate about, trying to delineate these circuits more. And here's an example of a VT circuit on the epicardium. This is a non-ischemic. And here we have the isthmus. These are the isthmus boundaries. And we've got a nice little clockwise loop turning around. The question is can this be complementary with entrainment? Of course. So we typically will try to get the activation map first. Then now here is the entrainment. We're going to pace here right where it's about to exit out, here where it's turning. And then as we would expect, we get concealed fusion. Pacing looks the same as down the road here. And then importantly, your stim to QRS is only 105 and your tachycardia cycle length is 530. PPI and the TCL are the same. Looks really good. You divide that 100 by 530, you're going to be less than 20%. That makes sense with the exit site. So I think it's kind of good to see activation with entrainment together. What about if you're in the central isthmus? So that would be somewhere here between these two goalposts. And here we have isthmus entrainment. Again, look at the area that's not captured. Look at the area captured, cut and paste. Perfect. Concealed, number 2, PPI TCL, 535. TCL 530 within 5. And then take a look at your stim to QRS. It's longer because you're pacing here, so it takes longer to get out to the exit site, which is your QRS, and that's 200. Divide 200 by 535, you're getting closer to somewhere that's around 40%. 50% again is kind of a mid-diastolic site. So that's the isthmus. Now, what about this little area? And then this again is just to show you that even there's beauty within the intracardiacs when you're looking at the multi-electrode. Here is concealed entrainment with intracardiac concealed fusion, that the shape of the way that this duodec is being activated, this V shape, is preserved during pacing as well as during the circuit, during the tachycardia. So here is really nice example of intracardiac fusion with every criteria. You could call that the fourth criteria, but we don't require that. And then the last one is the red area that I have here is indeed an attached bystander. It's going up through the circuit, but this is that little pouch that's a dead end. What would happen if we try to entrain within that pouch? Here you go. Bystander site, pacing within this red area. It has to get onto the racetrack, which means that there's a longer stim to QRS when you're pacing. And that's why the stim to QRS here is 200. It is concealed though, because it's attached and it can only go out the exit site because it's a blind loop. The important thing here is that that excess of the PPI minus TCL of 660 minus 530, because again, it goes out to the racetrack, does one revolution, and then has to go back in to get sensed again. That difference, 660 minus 530, is 130. That is the same difference as the excess of the stim to QRS 200 and the EGM to QRS of 70. And we'll talk a little bit about that if we have time about the math. But that is always preserved because the distance from the blind loop to the circuit is the same every time. And then more interestingly, and more proof that this is a bystander site by activation. Many people will say, well, you can't use activation mapping to tell bystander. Well, here you can see that the blue does not propagate all the way out to the purple. So you can actually see where there's discontinuous isochronal activation, that there actually is a bystander by just activation alone. Here's even a nice phenomenon. You can see that while we're recording from that site, you have activation, activation, activation. Oops, there is not any local recording there during VT, which tells you that block into that bystander does not have anything to do and is not a critical site for that VT to continue. So that's a really nice example of a bystander activation by every single criteria you can have: entrainment, activation mapping, and then block into it with continuation of tachycardia.
Hey, Rod.
Yep.
Phil Kukulich had a question here. He said,
Yep.
Can you discuss how you can rapidly determine the exact timing of each local EGM activation when they have multiple components?
Oof. I can't do that rapidly, Phil. We'll get to that right now when there's multiple. Obviously, I'm starting with simple, but we're getting to multiple really, really quickly here. Hold that thought for a second. Okay, question number one. Let's go through some. This is where I would ordinarily pimp some of the fellows. How are we doing on time? What time is it right now?
Getting close to 8.
Okay. We're doing an hour in a shot?
That's the plan, but honestly, I mean, if people
fine.
want to stay on and you want to go a little further, that's not.
I think we're doing fine. 7:54. So here we go. Here's question number one. Fellows, is this a good spot? Should I come on RF? Think about it, let it percolate for a moment, and then I'm going to discuss it for you so you can actually enjoy yourself. Immediately, keep looking around. Tell the fellow to pace faster. Start screaming out there. Tell the fellow to pace slower. He's pacing too fast. That wouldn't be good because if you pace too fast, which has actually been shown with CTI, next time you get a CTI case, pace it at like 160 and see what happens. And many of the times the PPI will artificially be way longer than you would if you were just 10 milliseconds under it. So we try to pace 20 milliseconds faster than it because 30 seems a little bit too fast, and 10, sometimes you can barely tell if it's capturing and you have to stand for a longer period of time. So in general, people recommend 10 to 30 faster. But while you guys are thinking about this for a moment, I'll go through it. So the first question is, one, start with the surface. Step one, is it a cut and paste job? Is it the same exact QRS? Well, I'm only showing you 5, so it's a trick question. But of the 5 that I have here, to me, it looks identical. So there's concealed fusion, assuming you're capturing. So it will always look identical if you don't capture, because it is the tachycardia. So then you got to measure and get your measurement tools out and see if 380 here, which you could see on the Pruka, if that's sufficient. And you can see that the stim to QRS is consistent. And if you were to measure this, this is faster. An eyeball test shows you that this last pace beat is a little bit maybe longer than here, but not much. So you've got to make sure you pace fast enough. The next question, which is what Phil's talking about, is I've got a lot of candidates here. How do I know which one I'm capturing? Well, that's the tough part. But the easiest way to do that is to work back from your QRS and say, from my QRS here, what is the electrogram that I'm interrogating? And I've got this option, I've got this option, I've got these noise options probably. You can see this is gained up. And I've got this other stuff in here. So there are multiple components, but our eyes gravitate towards the largest one. And that may or may not be a good thing. But let's go with that, because we always say high frequency signals are near field and low frequency are far field. And nobody in the world knows how near is and how far is. But for the sake of just this interpretation, let's go with this component or this one. Well, this one here is not captured, because if you captured this one, then your stim to QRS should be this long. So obviously you have to look at your stim to QRS as a reflection, as a quick marker to be able to tell which electrogram to QRS you're capturing. And if my stim to QRS is this, then I'm going to start back from my QRS site and march back down this slope and look for something around here. So here it is. I'm starting here. I'm going to march down there, look for something in this area, come down. Oh, and it's this one. And then you want to make sure that's captured, that you're not seeing this repeated electrogram throughout. And I don't see this one here at all. And you could say, well, wait, I see stuff here, I see stuff here, but that's all under the QRS. So what we're going to do here is just to step one, it's concealed, it's not overt. Check 1. 2, PPI equals TCL. Let's go to that electrogram. 440, 430, 10 millisecond excess, fine. Step 3, let's test the theory if we approximated the right component of the electrogram. Let's work backwards from here to there is about 114. Well, then let's work backwards from here to there. That must be the component I'm capturing because the stim and QRS is the same. Okay, so all 3 points are satisfied. So if you guessed come on, you were right. Are there any questions with that interpretation before we go to the next? Any questions, comments? Okay. Question number 2, remote bystander, isthmus. This is like perfect board style. 1 simple tracing, 4 simple options, go quick. Step 1, you got to be asking yourself, is this concealed or is there overt or manifest fusion? Step 2, look at the PPI TCL. Here's an easy one. It's only 1 component, electrogram. There's only 1 candidate. So that's easy. And then you got to match up your stim QRS and EGM QRS to answer the question. So I'll take this. Look at the 4 surface leads. Is it a cut and paste job? Absolutely not. You see the notching there in AVF. You see it looks flattened there. You see it's broad here in 1. It's not the same. I'm sorry, there's 4 surface leads. There is evidence of overt or manifest fusion. So which options cannot be correct? Remote bystander, isthmus, outer loop, adjacent. Well, adjacent is attached to the circuit and only can exit the exit. So that has to be concealed. Outer loop has manifest, remote bystander has manifest, and isthmus is concealed. So you can take away options B and D with this based on only the surface. You haven't even looked at the PPI TCL, which is what everyone goes to first as step one. It should not be step one. Just look at the concealed versus manifest, and that'll guide you very quickly. Now all you have to deal with is outer loop versus remote bystander. And if you look here, your PPI TCL, there's the overt fusion on all 12, is 510 to this electrogram of interest, 501. So is that a remote bystander? No, because you are very close to the circuit, if not on the circuit. You're within 30. So therefore, the answer is outer loop. Does that make sense to everybody? Any questions on that? Now's the time to ask. Manifest fusion, PPI equals TCL, and then if you play the EGM to QRS third criteria, this to this is super short, and this stim to QRS is super short. So the EGM and stim to QRS are the same. And if you were to look at that graphically, you would see a circuit that's going around here. The stim to QRS is really short, which means you're very close to the exit site, but you're pacing somewhere that is not completely confined and protected by fibrosis. So you still get antidromic fusion out here. So that's the typical outer loop response. Does it mean you can't terminate VT? No, you could, but think about it. If your VT circuit's going around and around here and you start burning on this asterisk, it's just probably gonna circumvent and go around you and maybe get wider. You might slow it, or you might not do anything because there is no barrier here to anchor to. Whereas when you're ablating within this isthmus, you hit one little spot here, and that explains why, 60 or 70% of the time we can get rid of these within one application. Okay, question number 3. What response is shown here? Now this is getting progressively harder. You might be like, Tung's wasting my time right now. This is a joke. This is all review. Well, the joke might be on you here now. So take a look at this, let it process. Okay, this is really hard. This is really hard. This is like attending level. Remote bystander, isthmus, inner loop, adjacent bystander. So let me slowly go through the process of how to attack this question. There's 4 surface leads. I've got ablation distal, ablation proximal, and an RV catheter. The first question I have is, am I even capturing before I even approach the 3 criteria? Well, the stim to QRS, the stim is in a weird place. It's inside the QRS, first of all. That's the first observation. And that looks weird because remember, if you're 30 to 70% within, then you should be somewhere in the middle of diastole, which is why I asked you guys and gals of where the middle isthmus is. It should be somewhere around here, which means when I'm pacing, the stimulus should be somewhere around here, and it's not. So I can already tell without even looking and going to make measurements that this is not a central isthmus. And that's really useful in clinical cases. If that stim is inside the QRS, you're not in the central isthmus now, but you could be in an entrance. So we'll talk about that. Now we have to ask ourselves if this is concealed or if there's manifest fusion. Well, I like lead 1 as a cut and paste job. I like lead 2 as a cut and paste job. I don't like V1, but I like V6. Only V1 doesn't look like the QRS during tachycardia, but it probably is because there's a stimulus artifact in there that's giving us that little fake tented up thing. So I really need to see all 12 leads, but all of it looks pretty good. How do I know it's just not the stimulus artifact and it's actually perfectly concealed? So it might be, and I think it actually is. So then the last part, which goes to Phil's question, is how do you rapidly, and of course Phil's very specific, how do you rapidly know which one it is? Well, I'm not going to rapidly be able to tell this one because this is tough, but let's go through this slowly. Here, there are 2 electrograms of interest, this one and this one. Larger amplitude, lower frequency, lower amplitude, higher frequency. Just aesthetically, by electrogram characteristics, most people would say, you know what, the near field is probably the one that's the sharpest. And that's not wrong. That probably will guide you correctly, maybe 70% of the time. So here, let's play that game and say, this is the one that is of interest. Okay, well, if this is the one of interest, then I should directly capture this one, and my stim to QRS when I'm pacing should be the same as this EGM to QRS here. This should be it. But if that's the case, then why is my stimulus in the middle of the QRS? It should be here. So that tells me this probably isn't the one I'm capturing. Okay, well then let's try this one. Ablation distal has this large component. If this is the one that I'm capturing, then my stim to QRS should be inside the QRS indeed, and it goes over to there. And that much more approximates what my stim to QRS is. Is everybody following that so far? If there's any questions, ask right now, actually. Any questions, including attendings? Okay. So this is where using your neighbors is really helpful. How do I know if I've captured this component? Well, look at proximal. You've got this really nice little sharp thing that then scoops down and gives you this negative component. Look at during pacing. On proximal, I see this little sharp descending pixels of electrogram with the same scoop up. Does everybody see that? It's right there, which means I'm capturing something here directly and orthodromically capturing this pretty immediately after the pacing spike. So this proximal is actually the key to this puzzle, that it actually is capturing something around here and not this component. So this is the one that we're going to measure to. So here are the 12 leads. Step one, it actually is concealed. It's just that one lead V1 because of the stim artifact that makes that strange, which is a nice little pearl. Step two, which component is captured? I see that little proximal is indeed captured orthodromically very quickly after the pacing spike. So I have to look somewhere beyond that interval, and that would be there. And also you can see where it actually is sitting in VT. It's absent during pacing, which means it is captured. It is brought in over here. So therefore you measure to this area, which is the onset of the QRS of the local potential, and it's 635. Ooh, that's 150 longer than the TCL. So that is most likely a bystander that is attached because it's concealed, so you know it's not a remote bystander. It has to be an adjacent bystander. And the reason why that's beautiful is because we couldn't tell which component was captured, but we used the neighboring to be able to give you, to guide you that you should measure to this electrogram. And then when you look at that, the stim to QRS is 315, EGM to QRS is 165. Look at that difference. 635 minus 45 is 150. 315 minus 165 is 150. Same. So why does that work that way? Well, here's the algebra. Here is pacing from within a blind loop. You need to get out of the circuit, out of the bystander to the racetrack, go around once and come back in. That's why that PPI is long. Let's look at them individually. One revolution is the tachycardia cycle length. The PPI is the tachycardia cycle length plus a distance X to get out when you're pacing from it, and then a distance X to go back in to then record it again. So it's pacing to get out X, and then that distance to be able to be sensed again. So that's why it's 2x. And I know it's a little early for algebra. If you look here, what is the stem QRS when you're pacing from a bystander? It's that same distance x, but then you also have to add a distance y, which is the distance that once you get on the racetrack, that point of entry, the exit, that's x plus y. And then when you do the math, and I'm not a mathematician, but here it is, when the EGM to QRS comes back into sensing for the bystander, this EGM to QRS is a pseudo interval. That's the most important thing. It's like the His bundle during bundle branch per entry. The His bundle is not part of BBR. You activate around below it, and then it also goes up to the His bundle. It's the same thing for a bystander. The TCL comes around, you got to go back into the bystander, and by the time you go into the bystander, the circuit is that distance closer to the exit site, and that's why it's y minus x. And that's very confusing, but when you do the algebra and you take x plus y minus x, it's the same difference as 2x, which is your PPR minus TCL. So I'm happy to send this slide out, but hopefully that is one time, once and for all, that difference is exactly the same. The stem to QRS, EGM, and your PPI TCL. Okay? Here is another example of a bystander using neighboring electrograms, concealed, step 1, step 2. I'm trying to figure out what's actually captured, because someone can mute their kitchen. And then here we have the multi-electrode catheter. And then this is MP34, which is what we're pacing from. You can see that. What's really cool about this tracing is the area that we're capturing here, look at it during activation. It's immediately to 5/6. But look at when we pace it, it spaces it out to 5/6. Everybody see that? So all of a sudden, my EGM to QRS during VT is different just between these two electrodes. And this is a long stem to this local. How do you explain that? Well, you explain that the activation actually doesn't even go from 3/4 to 5/6. That's a pseudo interval. We have this tendency that if one electrogram is earlier than the other one in EP, we draw an arrow from the earlier one to the later one. That's not the way it always works. It just means that's relatively earlier, but that could be a pseudo interval. It doesn't mean you have conduction between 3/4 and 5/6. So this is the perfect example in which 3/4 is a bystander and 5/6 is on the racetrack. It is on the circuit. And during the tachycardia, your sensing of 3/4 is occurring almost simultaneous with 5/6, which gives more credence to the idea that that's a pseudo interval. So let's take a look at that. This is 685 to 3/4, no good. This is 565. So that is a long PPI minus TCL of 120. The EGM here locally is much shorter than it is during pacing. So this, you probably haven't seen before, is a multi-electrode demonstration of one electrode being a bystander and the other one being the isthmus, and being able to record both activities at the same time. That's what's special about this tracing. How does that look if you can't conceptualize that graphically? Here, this is the VT circuit. It's coming down. This is an anterior infarct ischemic cardiomyopathy, and it rotates back up figure of 8. There is a huge blind loop. Let me play that again. There's a huge blind loop right there. That part's not needed. So if your catheter is laying across the isthmus and the blind loop, you could be sensing both blind loop and isthmus. So this is one of the electrodes. This is another one. It's so close. These are 2 millimeters apart on a duodeca. That's 222. And what you have here is that when you're pacing from here, you have to get to this from the bystander. You have to get to the circuit, which is why all of a sudden the electrogram is longer during pacing than when it's sensing. But when you're during VT, it's a pseudo-interval. It's sensing the green, and it's also going to red. Hopefully that makes some sense. I know that's a novel concept to be able to see both at the same time. But again, let's say this is green, and this is red. When you pace from green, that interval gets longer. Are there any questions on that? I told you it would get progressively more complex and progressively more weird. Any questions? Big blind loop, big bystander, differences there, okay? All right, this is borrowed from the late Mark Josephson. I stole it exactly, didn't even try to change it to honor him. Mechanism of VT is not macro-reentrant. That's the number one. Everyone always says, did you guys do entrainment? What they mean to say is, did you do overdrive pacing? And if you've read anything by Waldo, you know there's 3 criteria. We almost never satisfy all 3. But you need to show progressive fusion, constant fusion, and then at cessation of pacing, the wavefront needs to change with the local electrograms you're recording. So you cannot assume that overdrive pacing means it's reentrant. We all know that, but that needs to be emphasized. Distinguishing local from far is the hardest thing to do, which is why we planted Phil there in the audience to ask the question, how do you tell with multi-electrode catheters? We're gonna get even harder right now. A large area of capture is a problem. In general, we don't typically pace at 2 or 3 MA in SCAR VT. We usually pace a lot like 10. Sometimes you can't capture. So that's a problem because it's really naive to believe that you are capturing only the local electrogram of your own interest. Oh, I see that little pixel. I'm going to dial up that pacing and capture only that. I don't think anyone's that good. And when you're pacing at high output, you're capturing much more than just the local potential of interest. And I'm going to show you evidence of that with multi-electrodes. Next, obscuring the EGM by pacing artifact. That's where this N+1 rule comes in by Sojima and Stevenson. We'll talk about that. Sometimes you can't see where the electrogram is after you're pacing. It's so noisy. Most people are not good enough. Not good at being able to decipher whether it's close enough or not close enough. And people say, well, it's almost concealed. If it's almost, it should be like pregnancy. You're either concealed or you're not. So there are no in-betweens, like it's pretty good. If it's pretty good, then there's overt manifest fusion. And then termination, acceleration are the reasons why at U Chicago, we're not really huge entrainment people because we're trying to delineate the circuit with activation first. So we don't want to disrupt it. Only when we have it perfectly do we say, do we want to entrain? All right, let's get something good for the fellows so we can review it. Then we do that. So our preference is activation over entrainment. So this is question number 4. What is the mechanism of this VT? Here's the activation. This is a Cardo map playing for you. And you can see that it looks like there's focal centrifugal activation on the epicardium. And there's the VT. Options are it's focal, automatic, focal triggered, micro reentrant. Who knows what that means? I've looked everywhere for a definition of that. There are no definitions. Or D, cannot tell. Let's play that again. And what I'm hoping the Job Logs answer here is that someone says this is focal. Because the point of this is that you cannot tell mechanism by the pattern of activation. How do you know that this is not mid-myocardial reentry on the epicardium that just breaks out the epicardium? So you cannot tell mechanism by activation maps. You can't tell, and if you see focal. If you see the whole circuit cruising around and you've got the whole cycle length, that helps you. But when it's focal, you cannot rule out reentry. You have to do entrainment maneuvers and show fusion. So here's how that would go. And this is something that I learned from John Miller. Here's the VT, 450. Overdrive pacing, 430. Does it look exactly the same? Of course not. We're pacing at a site in the RV for an LV VT. That's the pearl. If you don't know the mechanism, pace very far away so your fusion will be so obvious. Take it, if it's left bundle, left inferior, pace somewhere from the right side where you're gonna get a superior axis. So you really will make fusion very obvious. So that's overdrive pacing at 430. This is it at 390. So this is the idea of progressive fusion, that when I pace faster, there should be less fusion and I should look more like RV pacing. And here is RV. When you assess fusion, you have to look at both parents to be able to see if the child looks something in between. You cannot say, here's a picture of my wife. Does my kid look more, I'm sorry, here's a picture of my kid. Does the kid look like me or my wife? If we don't know what your wife looks like, I can't tell you that answer. You have to have pure pacing and you have to have the VT and see that it's some fusion of in between. And when we go faster, it should look more like pacing. And when we go slower, it should look more like VT. So this is a perfect way in which a quick overdrive pacing, you can look at this clinically when you're ATPing someone out of the lab. And after you get the patient out, then pace from the site of ATP, and then you all of a sudden have the ATP overdrive, you got pure pacing, and you got the VT. And then you'll know the answer. So this is a really important pearl, and you'll know the mechanism of VT before you even put catheters in. You can do it from the ICD. So that's fixed and progressive fusion. No entrainment talk is complete without the N+1 difference. This is from Sojima now 19 years ago. The idea is predicated upon the fact that you get these huge saturation. Here you can see they've clipped on ablation 1-2. You can see they're guilty of clipping it. You would see this huge thing there, and then there you cannot tell the local electrogram as clearly as maybe 3 cycles down the road. And the idea was that if you take any fiducial point from the QRS, just like we work back from it, we can then be able to tell if the stimulant and EGM and QRS are the same. And the whole point is that S to QRS +1, which means just go to the EGM, forget the EGM, go to the QRS, then go somewhere downstream to that QRS and take that same interval and come back and see if that electrogram is there. That works just as well if you cannot see the electrogram of interest after pacing, okay? And that difference is gonna be the same, that N+1 difference. So the citation is there, it works for dead-end pathways as well, okay? I think with the remaining 7 minutes, I've got 2 or 3 other challenging ones, so we'll walk through those quickly and we'll conclude for questions. Should I come on RF here? Immediately keep searching, pace faster, pace slower. First thing I wanna say is there concealed fusion? Well, it actually looks pretty good, but again, we've got that same issue where the pacing is inside the QRS. So if it's in the QRS, it's got a long stem to Q, or maybe you're actually not even capturing. So this is one of the most important parts. And everyone gets fooled by this. I guarantee you're gonna have a time where you think it's perfect, but you actually didn't capture. And this is that scenario. You're not pacing fast enough. How do you know? Look at the local electrograms. If you directly capture that electrogram, you should no longer see it anymore. It should not be waving at you in diastole. So while you're pacing here, if I'm capturing this directly, this should not be sitting there. It should be recruited into the stimulus. So I'm not capturing this, so I can't measure my PPI to this. I'm not capturing the onset of this. The only thing I could be capturing is this broad DVDT as an option. And when you look here, I'm pacing at 480 and this is 480. And it looks perfect. And that's the whole point. It will always look like the VT because it is the VT. It's not even captured. So that's a really important limitation to throw in there as a curveball. Okay, progressively more challenging. What response is shown here? How am I going to attack this? I've got 12 leads. I've got 1 ablation catheter, distal and proximal. I have 2 components of interest. I've got to play out both scenarios. First, am I concealed? I believe I am. I think it looks identical. Am I captured? I believe I am. If we measure this, and you can do that offline, it is accelerated to the pacing cycle length. Now my task is to figure out if it's this or if it's this that's captured. Well, again, look during pacing. Which one is no longer seen? That is the one that is directly captured. Well, I don't see this big one during pacing. It's no longer there. But I still see the small little guy right there. And it's there, and it's there. So this is orthodromically captured downstream, but it's not directly captured. So you have not interrogated that local electrogram component to be able to assess that location's circuit property. All you know is that you're capturing something that's not that, which is most likely this. So that's really interesting, because then we measure the PPI to that, and then let's look at our numbers here. If we measure stim to QRS is long 290. This component is the one that we actually believe we're capturing. The EGM to QRS is 255. So that's about 35 longer. And when you do your PPI in TCL and you go all the way to this component, it's also 35 longer. So that's actually a bystander response. Bystander. But you're recording the isthmus site, but you're not capturing the isthmus site or the candidate isthmus site. So here's a perfect example where you have two components, can't tell which one you're capturing, but by looking in the pacing train, whichever one is saying hi to you, what's up, you haven't touched me, that one is not directly captured. But it's orthodromically captured because you're accelerating it downstream. So this is a simultaneous recording of an isthmus that you can't capture, but you actually capture the larger component of the bystander. It fundamentally highlights where sometimes we can't selectively dial in the electrogram of interest. That we don't care about the one that's in the QRS. I wouldn't care about that. I'm interested in the one that's that's in diastole. But I can't capture that one because it's so small, the amplitude. So that's actually a pitfall of entrainment mapping, is that sometimes you can't even capture the electrogram of interest. And then here, ablation comes on at a site that you, by entrainment, actually could only show it was a bystander, one of the components, and then it goes away in 5 seconds. Okay? All right. Here, maybe second to last, we'll whip through this one quickly. What is the problem with this entrainment? Am I even capturing? Well, what's weird is the stim to QRS kind of keeps changing. That's weird. And if you look at it, when I stop pacing, the TCL has some oscillation here, folks. That's not a good tachycardia to do entrainment for, because you have natural oscillations. So am I going to be measuring my PPI to the shortest TCL or to the longest TCL? Or am I going to try to play the game of seeing if there's periodicity to it and then try to see where in the periodicity, but then I got to capture multiple beats? This is the perfect example of where entrainment is essentially impossible to interpret. Here it is. Stim to QRS is 130, 240. Pick whatever you want. It gets longer and longer. You get all these variations. This is what happens when you have a very sick decremental conduction within the isthmus, and you can get a very long PPI. Don't know which one to measure to, but I'll tell you, it's probably a pretty good spot, because you're getting decremental activation during tachycardia cycle length and you're getting it during pacing. But this is not one that's going to be able to fulfill normal fundamental principles. Okay. And then here you got the oscillation. We come on ablation. You can see ablation on, boom, gone like a pathway. So, but that again was not demonstrated by entrainment mapping. What response here is shown? So here, and I think we'll conclude with this tracing, is I'm giving you one channel. How do I know I got multiple components? I've got here, and I've got this one. Well, again, I need to look to see if I capture this one, my stim should be inside the QRS. If I capture this one, my stim should be somewhere here before the peak of the T wave. Well, my stim here is way before the T wave. So I might not be capturing any of those directly. So then you start thinking about a bystander situation. Well, this is interesting. I see a little bit of fuzz, and this is real world. Because if someone were to measure this, they would be like, nah, that's noise. But I see some fuzz here, and that's a big difference between this and this. That's 357. Now let's use the neighbors. And this just highlights the last point that I wanted to make, which is that we capture much more than what we intend to. If you look at the neighbors, I see there's also a component here before it, and that is 310. Here is the entire circuit, all of diastole. And I was only interested in this middle electrogram, but look at what happens to the electrogram above it. Here, all of this is captured as well, because the only thing you see is this last component, which is this third component. Component 3, 2, 1. You're capturing 2 and 3 because it's gone, and you're likely capturing 1 because it's also gone. And if you go one more up above it, you can see these electrograms are hanging out right there. So the point is, this is multi-electrode evidence that we're capturing way more than we want to.